So we recently received a new RF meter, EMF meter, to test. So we're going to find out if it lives up to its claims. And we're going to find out at the same time we do.
Yes, so this is the...
Deutschland.
It's a Cemprotec 34, and it's an RF E-field and mag field detector. Today we are going to test some basic RF functionality. We're going to do a pulse width test, and we're not going to do a continuous sweep frequency test, but we're going to just pick a few test frequency, what goes on. This version that we received, the manual is all auf Deutsch in German, but that's okay. I'm familiar with that. And a quick look, it looks like it's a very sensitive device. RF on the RF scale, the fine RF scale that lights up all the LEDs, can go up to 2,750 microwatts per square meter. So that is geared for, obviously, presumably measuring very sensitive levels. So let's find out what this thing does at different frequencies and power levels, all right? Mm-hmm. Okay, we're in the control room right now. So our usual setup, we've got the HP signal generator, 2.4 gigahertz. Our test power level for the pulse width tests are going to be the usual 1,000 microwatts per square meter. So we've got the signal generator coupled into a Rigel function generator, and we usually start off at 100 microsecond pulses to see what's going on. And going up to the closed circuit monitor up there. So we're in the reverberation chamber. The RF stirrers are not working or not turning right now. We don't need the RF stirrers for pulse width tests, since we don't care so much about power, it's just we're measuring the response. So according to the documentation on this meter, having this many LEDs lit is equivalent to about 1,000 microwatts per square meter. We have a Pro 2, a Safe and Sound Pro 2 in reference sitting beside just to see an indication of pulses. And it's only showing just about 500 microwatts per square meter. Now again, because the RF stirrers aren't turning in the chamber, there's going to be a difference in a reverberation chamber. There's going to be a bit of a difference with different positions. Obviously we can't have the antennas in the exact same point in space together, at least not easily. So anyway, I just wanted to give you that example. So this is a CW continuous wave source, just to get our power level set. And now I'm going to actually do the trigger at 100 microseconds. So the signal generator is off right now, and a manual trigger is right now. And we saw the Safe and Sound Pro respond. I'll do another trigger right now. It didn't really respond. I thought I saw one LED on the bottom, the third LED. Another pulse now. Okay, so unfortunately this meter is not even seeing 100 microsecond pulses. So we obviously have to increase the pulse width in order to see the response of this meter. So I'm going to dial it up to 500 microsecond pulses, and here we go with 500 microseconds right now. Okay, it saw that one, but very low reading. Again, now. A little bit higher reading, again, now. So really, at 500 microseconds, I'm seeing a total of 6 LEDs, which indicates only 40 microwatts per square meter. So this meter is measuring a pulse, but it's, it's really not very sensitive. So I want to see the pulse width at where it's able to detect the power really accurately. Wow, so we're at 500 microseconds right now, and it's performing very poorly. Keep in mind the new AM11 and our Safe and Sound Pro, they measure very accurately at 5 microsecond pulses, and we're 100 times slower, and this meter still isn't reading that. So I'm going to go to CW here again, and I'm going to dial up the pulse width to 1,000 microseconds or 1 millisecond, and we're going to do a manual trigger. Here is 1 millisecond. Now, wow, it's still showing low. And again, now, oh, it showed 9 LEDs there. And again, now, oh, we got 10 LEDs there. How about another one? Now, yeah, we got 11 LEDs there. Another one. Yeah, okay, so 10 or 11 LEDs are indicating somewhere around 180, 200 microwatts per square meter. So still quite concerningly low, considering that we want it to see 1,000 microwatts per square meter. Okay, powered up. So we continue now. We're about to send a pulse of 2,000 microseconds or 2 milliseconds, a very wide pulse. So here's the pulse right now. Bang. Okay, so I saw 10 LEDs there. Again, now, now we're starting to see something. Again, now, okay, so again, now, okay. So we're catching close to most every pulse. I'm just going to randomly trigger some pulses here, and so it looks like, yeah, it looks like around 2,000 microseconds is where this meter starts to be able to detect pulses. So unfortunately, if you're going to use this meter for any narrow pulse width or high-speed digital sources, it's not going to be very effective. So that's too bad. Again, other meters are quite capable. Even a lot of meters are on the market are capable of 100 microsecond. You know, more than 10, 20 times as fast response. So very disappointed in this. Let's poke, turn on the RF stirrers and do some just some frequencies and see how accurate the frequency response is of this. Okay, so right now we are at 2.4 gigahertz. As you can tell from the shimmering light, I think my hand is getting in the camera there, is it? Yes, okay. Kayla's smiling, so I guess so. You can tell from the shimmering light that we've got the RF stirrers rotating, and we're at 2.4 gigahertz, and we want the meter, we're expecting 1,000 microwatts per square meter at that. And if we see right now the most amount of LEDs, you have to count. You have to count that. Maybe Caleb will probably show a picture of this RF chart in the video. But according to this many LEDs that are on right now is 1,000 microwatts per square meter at 2.4 gigahertz. So very good. We're now at 800 megahertz, and we expect, again, we expect a total of they count, it's a bit confusing, they count the first LED as LED 0, so they say 16 LEDs is 1,000 microwatts per square meter, so 17 LEDs, but we're getting 22 LEDs at its peak, considering there's a maximum of 24 LEDs, so 22 LEDs. It is about, that means it's about a little over 2,000 microwatts per square meter, 3 dB difference, so that's fine. So it is responding very sensitive at 800 megahertz. Let's go in the opposite direction right now. Let's start going up. Okay, so we're at 3.0 gigahertz, and again we're expecting 16 LEDs or 17 LEDs. Again, confusing. But right now we're seeing a total, at the peaks, we're seeing a total of 8 LEDs light. So that corresponds to about 75 microwatts per square meter. So it's measuring a little low there, but at least it's measuring something. Okay, we're at 4.0 gigahertz right now, and we are seeing a total of 3, 6, 9, 12, a total of 15 LEDs at its peak. So that's not bad. That is, according to this, including, so it's actually including zero, it's around 550 microwatts per square meter. So very good performance at 4 gigahertz. We're at 5.0 gigahertz, and again, very good response from this meter, as you can see on the screen. If we count the amount of LEDs, so 24, 19 LEDs at its peak, maybe 20. Did I see the 20th? So 20th LEDs. So again, right now 1500, 1750 microwatts per square meter. Again, fantastic sensitivity at 5 gigahertz. Let's go to 5.6 next. Okay, we're at 5.6 gigahertz, and again, very good performance. It's a little more sensitive right there. So we're up close around the 2000 microwatt per square meter, but again, very sensitive. You know, I didn't expect to go, but let's do 6, 7, 8 gigahertz. Let's just keep going up. Okay, we're at 6.0 gigahertz, and again, great sensitivity. The meter is still, it's very sensitive, doing well. Let's go to 7. Okay, we're at 7.0 gigahertz right now, and again, reasonable performance here. So we've got 3, 6, 9, 12, 15, 16, 17 LEDs, 16, very close to 1000 microwatts, so very good. Let's go up to 8 gigs. Okay, at 8 gigahertz now, we are seeing a total of, at the peaks, a total of 6 LEDs. So we're down to about 40 microwatts per square meter. So it's looking like the response is starting to drop off before 8 gigahertz, but again, it's still measuring something. Let's pop up to 9 gigahertz and see if we get anything at all. Okay, we're at 9 gigahertz right now, and we're just seeing about 3 LEDs light up at the peak. So that's about 2.5 microwatts per square meter. So it's rolling off. The specifications for this meter are from 1 megahertz to 10 gigahertz, which I find hard to believe. We can't test below 200 megahertz. We don't have powers documented, or the chamber hasn't been calibrated for that. But certainly a response up to 10 gigahertz doesn't look like that's happening. But up to 8 gigahertz, reasonable performance. Again, we didn't do all frequency points, but we get a general idea that it is responsive in the Wi-Fi bands, and certainly pretty good up to 8 gigahertz. So for detecting CW signals, pretty good meter, but pulse width, not great. And just an extra little test, we're going down to the lowest calibrated frequency we can do. So we're at 200 megahertz right now. We're still seeing the same thing as before, as what we saw at 9 gigahertz, is that the third LED lighting. So it's down to a couple microwatts per square meter. So not very good at the bottom end. Now there could be another antenna, another detector for lower frequencies. Don't know in this design, but now we have a better idea. Okay, so there you have it. Yeah, it's pretty good, for frequency response. At
goes up pretty high, but does not go down very low.
Yeah, and the pulse width is very disappointing. So looking again at this single page German print out instructions. There's no specification for pulse width detection, so maybe it's an unfair test. Maybe they don't expect it to be.
Right.
Although they do say it's a detector for 3G, 4G, and 5G. And so, I mean, especially if you're
5G
talking 5G,
is generally narrow
4G,
pulses.
yeah, it's fairly narrow pulses, even 4G. So you want to, you know, have some ability to have narrow pulses. So again, if you're expecting to use this meter, at least the current version that we have, with devices like smart meters or smart appliances that do random pulses, it's not going to be helpful at all. I guess maybe we can do another video if we want for the mag field performance, something like that. We can do that test.
Bust out the Helmholtz
But yeah, kind of confusing interface a little bit, hey?
Oh my goodness. So a bunch of LEDs you have to count and then look at the chart to realize what the LEDs mean. Right.
Now again, so this gets into the thing of, you know, do you want a specific display that measures a number? And we might do a video on that in the future. To me, it's nice to have the availability of numbers, but in the grand scheme of things, when I'm going into an unknown environment...
Good. Thumbs up, thumbs down.
Thumbs up, thumbs down.
Thumbs
I just kind of know, getting back to something as simple as like the Safe and Sound Classic, like just a few LEDs, or the you know, the upcoming Classic 2 with 10 LEDs.
8.
Excuse me, I keep thinking it's 10. I'm one of the designers and I don't even know how many LEDs it has.
It's got more LEDs.
More LEDs than 4. How about that? And to be honest, you walk into a space and it just, you look at the amount of LEDs and that gives you an idea if you're in trouble or not. So from that respect, it's you know, there are a lot of LEDs and you can see obviously more LEDs is more RF, right? But if you are a person that wants to actually know specifically, then you have to be good at counting LEDs. So this isn't the device for you. And if you're that kind of person that wants that accuracy, then you probably want a meter that can actually measure narrow pulses as well.
Yeah.
Again, this is the version that we had that was sent.
Perhaps it's a Ref 1 and it's a prototype and they haven't fully finished testing it. So.
Right, but good on them for the frequency response so far. Anyway, at least it's usable for sure.